So good morning, students. So I started till 14th we have discussed. So let us move to question number 15. The relation between frequency nu, wavelength lambda, and velocity of propagation of wave nu is. So we have this relation v is equal to f lambda, where f is the frequency, v is the wave velocity, and lambda is the wavelength. So in this present question, instead of f, you put f is equal to nu. V is equal to nu lambda, or nu is equal to v by lambda. So therefore we get option C. So nu is equal to v by lambda. So it's the correct option for question number 15. Question number 16. Velocity of sound in vacuum is. Sound is a mechanical wave. So it requires a material medium for its propagation. So since it requires a material medium for propagation, sound cannot propagate through vacuum. So therefore velocity will be equal to 0. So therefore A is the correct option for question number 16. That is, velocity of sound in vacuum is 0. So question number 17. The equation of a progressive wave is given by y is equal to 5 sine 100 pi into t minus 0.4 pi x, where y and x are in meter and t is in second. So now let us find out the parameters one by one. So let us consider the standard equation. So given equation is y is equal to 5 sine 100 pi into t minus 0.4 pi into x. So just compare this equation with the standard equation. Y is equal to a sine omega t minus kx. So on comparing the given equation with the standard equation, omega, it comes out to be 100 pi radian per second. So omega can be replaced by 2 pi f is equal to 100 pi. F is equal to 100 by 2, so we get 50 hertz. That is a frequency. And when you compare the relation from this equation, you get amplitude as 5 meter. So option A is given as the amplitude of the wave is 5 meter, and option 3, the frequency of the wave is 50 hertz. So let us find out what is the wavelength and velocity. So now k is equal to 0.4 pi. 2 pi by lambda is equal to 0.4 pi. Pi and pi gets cancelled. You get lambda is equal to 2 by 0.4 or 20 by 4 is equal to 5 meters. Wavelength is 5 meters. So it is given that the wavelength of the wave is 5 meters. That is the second option. And let us find the velocity. V is equal to f lambda. V is equal to frequency is 50. Wavelength is 5. So therefore we get velocity as 250 meter per second. And the fourth option is the velocity of the wave is 250 meter per second. So therefore, given all the options, that is 1, 2, 3, 4 are right. So therefore, which of the following statements are correct? Since all the given statements are correct, so we get the option D, that is all are correct. So we have found out all the parameters. So we have found out the amplitude, wavelength, frequency and velocity. So all the given statements are true. So therefore the correct option is D. All are correct. Question number 18. A stone is dropped into a pond from the top of the tower of height h. If v is the speed of sound in air, then the sound of a splash will be heard at the top of the tower after a time. So since it is dropped from top of the tower, so initial velocity u will be 0. And here let me equate s is equal to h. For this relation s is equal to ut plus half gt square. So h is equal to, since initial velocity is 0, half g into t square. Let me consider the time as t1 now. t1 square is equal to 2h by g. t1 is equal to square root of 2h by g. This is a time taken for the stone which is dropped from height h. That is dropped from the top of the tower of height h. Now this is the time taken. Now it is given that the sound of splash will be heard at the top of the tower after a time. The stone is dropped into water into pond. This is the time taken by the stone just to reach the surface of water. Let me consider this one as T1. Now if you want to perceive the sound at the top of the tower, so now I should consider another T2, which is given by h by v, because v is the speed of the sound. T1 is the time taken by the stone just to reach the surface of the water of the pond, and once it reaches the surface of the pond, so it generates a sound. The time taken by sound to just reach the person on the top of the tower, it should be taken as T2, that is equal to h by v. So therefore the total time it is taken as T1 plus T2, that is equal to square root of 2h by g plus h by v. So we get option A, that is the square root of 2h by g plus h by v. Next, let us move to question number 19. At what temperature will the speed of sound in air be 3 times its value at 0 degree Celsius? So in the synopsis we have studied the effect of temperature on speed of sound in gaseous medium or in air medium. So V is directly proportional to square root of absolute temperature T plus 273. So now let us consider at 0 degree Celsius, it is V proportional to 273 because small t is taken as 0. At what temperature will the speed of sound in air be 3 times its value at 0 degree Celsius? Now at 0 degree Celsius, I have considered the speed as V. 3 times V, let us consider 3V, it is proportional to at what temperature? T plus 273. So now we are supposed to find this T value, where the speed of sound, it is 3 times its speed at 0 degree Celsius, therefore 3V proportional to T plus 273. V is at 0 degree Celsius, therefore in the first equation I have considered T as 0. Now it should be 3 times the speed at 0 degree Celsius, it is 3V, we are supposed to find the T value. 3V by V is equal to square root of T plus 273 by 273. V and T gets cancelled. Let us square on both sides. Squaring on both sides, 9 is equal to T plus 273 by 273. T plus 273 is equal to 9 times 273 minus 273. T is equal to, since this is 9 times and this is 1 time, T can be taken as 8 into 2, 73. So 8 into 3, 8 3s are 24, 2, 8 7s are 56, plus 2, 58, 5, 8 2s are 16, plus 5, 2184. Therefore, temperature T is equal to 2184 degree Celsius. So therefore, we will get option C here, 2184 degree Celsius. Newton assumed that sound propagation in a gas takes under. So Newton assumed that sound propagation in gaseous medium, it takes place at a constant temperature. That is nothing but isothermal process, or it is a isothermal condition. Isothermal condition. Let us move to this question number 20. Newton assumed that sound propagation in a gas takes under. So A is isothermal condition, B is adiabatic, C is isobaric, and D is isentropic condition. But Newton considered that sound propagates in a gaseous medium at constant temperature. In the sense, it is nothing but isothermal condition. So therefore, correct option is A. So let us move to question number 21. A hospital uses an ultrasonic scanner to locate tumors in a tissue. The operating frequency of the scanner is 3.2 megahertz. The speed of sound in a tissue is 1.6 kilometer per second. The wavelength of sound in the tissue is. So we are supposed to find what is the wavelength of sound in the tissue. So given the frequency and velocity. So frequency, it is given as 3.2 megahertz, 3.2 into 10 power 6 hertz, and the speed of sound in the tissue. So V is given as 1.6 into 10 power 3 meter per second. It is given as kilometer. So when you convert to meters, it becomes 1.6 into 10 power 3 meter per second. So we have the relation V is equal to F lambda. Lambda is equal to V by F. V is 1.6 into 10 power 3, 3.2 into 10 power 6. 1s are 2s are. So you get 1 by 2 into 10 power minus 3. 1 by 2 is 0.5 into 10 power minus 3 meter, or it is 0.5 millimeter. So therefore the correct option is B. It is 0.5 millimeter. That is the wavelength of sound in the tissue. 0.5 millimeter. Option B. Question number 22. A 10 meter long steel wire has mass 5 gram. If the wire is under a tension of 80 Newton, the speed of transverse wave on the wire is. So for this problem, we are supposed to use the speed of transverse wave in a string. So speed of transverse wave in a string. So it is given by V is equal to square root of T by mu, where T is the tension and mu is linear mass density, that is mass per unit length. In the present problem, tension is given as 80 Newton, mass per unit length, that is M by L, mass it is 5 grams, 5 into 10 power minus 3 kg, convert gram to kg. Next length is 10. So mu is equal to, so you get 5 into 10 power minus 4 kg per meter, that is mass per unit length or linear mass density. V is equal to square root of T. It is given as 80 by 5 into 10 power minus 4. V is equal to square root of 16. Ones are 16 times 16 into 10 power minus 4. Sorry. this power it should be in the denominator. So it is 5 into 10 power minus 4. This becomes plus 4. So now root of 16, 4 into 10 power 2. Square root of 10 power plus 4 is 10 power 2. So you get 400 meter per second. So that is the speed of transverse wave on the wire. So therefore we get option C, the 400 meter per second. So here tension T is given as 80 Newton. So first you find what is its linear mass density, mass per unit length. That is mass is given as 5 grams. It is 5 into 10 power minus 3. Length is 10 meter. So therefore you get 5 into 10 power minus 4 kg per meter. So just substitute this value in this relation, you get 80 by 5 into 10 power minus 4. 5 ones are 5, 16s are. So therefore you get 16 into 5, 80. So therefore you get root of 16 is 4 and root of 10 power 4 is 10 power 2. Therefore you get 400 meter per second. According to Newton's formula, that is question number 23. According to Newton's formula, the speed of sound in air at STP, standard temperature pressure. So take the mass of 1 mole of air is 29 into 10 power minus 3 kg. So that is according to Newton's formula. According to Newton's formula, speed is given by gamma P by rho. Gamma is 1.4, pressure 1.013 into 10 power 5 Pascal. Density is 1.293 kg per meter cube. Already we have discussed and we have found the value of speed of sound in air using Newton's formula as, so it comes out to be 280 meter per second. So consider gamma as 1.4, pressure at 10 TP, that is 1.013 into 10 power 5 Pascal, density 1.293. Upon substituting all the values in this equation, the speed of sound in air using Newton's formula, it comes out to be 280 meter per second. So therefore we get option D. A progressive wave is represented by y is equal to 5 sine 100 pi into t minus 2 pi x, where x and y are in meter and t is in second. The maximum particle velocity is there. They have not asked the wave velocity, it is maximum particle velocity. So as the progressive wave propagates in a material medium, the particles of the medium execute simple harmonic motion. So therefore you are supposed to find what is the particle velocity of a particle executing SHM. Y is equal to 5 sine 100 pi into t minus 2 pi x. So let us compare this equation with the standard equation. Y is equal to a sine omega t minus kx. A is equal to 5 meter. So it says that x and y are in meter and t is in second. So therefore A is 5 meters amplitude omega. So it is 100 pi radian per second. We are supposed to find the maximum particle velocity. That is the velocity of a particle executing simple harmonic motion. It is given by V is equal to omega into root of s square minus y square. In case of a particle executing SHM, velocity is maximum at the mean position. So therefore y should be taken as 0. Therefore we get maximum velocity as V maximum is equal to omega into A. So therefore this is equal to, so omega is 100 pi into amplitude 5. So therefore we get 500 pi meter per second. There is a maximum particle velocity. So therefore we get the option as D, 500 meter per second. So it is not the wave velocity. In this it is also particle velocity. So as the wave propagates through a medium, the particles of the medium execute simple harmonic motion. So therefore we are supposed to find the velocity of the particle executing simple harmonic motion. In this present problem they have asked to find the maximum particle velocity. So velocity of a particle executing SHM, it is given by V is equal to omega into root of S square minus y square. Velocity is maximum when the particle is at mean position, that is y is equal to 0. Therefore V maximum is omega into A. Upon substituting the values you will get back the value as 500 pi meter per second. If Vrms is RMS speed of molecules in a gas and V is the speed of sound waves in the gas, then the ratio Vrms by V is. Question number 25. If Vrms is the RMS speed of molecules in a gas and V is the speed of sound waves in the gas, then the ratio Vrms by V is. So the RMS speed of molecules in a gas, it is given by square root of 3p by rho. That is RMS speed of molecules in a gas. V is the speed of sound waves in a gas. V is equal to square root of gamma p by rho. So this is the speed of sound waves in gas. This is the RMS speed of molecules in a gas. So now we are supposed to find the ratio. Vrms by V. So Vrms by V is equal to square root of 3p by rho into rho by gamma p. Rho and rho, p and p gets cancelled. You get the ratio as root of 3 by gamma. So therefore you get option A, square root of 3 by gamma. So the RMS speed of molecules, it is given by square root of 3p by rho, and the speed of sound waves in the gas, it is square root of gamma p by rho. So upon taking the ratio, it comes out to be square root of 3 by gamma. So that is the first option, that is option A. The speed of transverse waves on a stretched string is question number 26. The speed of transverse wave on a stretched string is V is equal to square root of T by mu, where T is the tension in the string and mu is the mass per unit length of the string or linear mass density. Directly proportional to tension in the string, but it is V is directly proportional to square root of tension in the string. Option B, directly proportional to the square root of the tension. Of course, it will be valid now. Option B, inversely proportional to tension, inversely proportional to square root of tension. Therefore, the correct option is B. So that is, it is directly proportional to the square root of the tension. Option B. Question number 27. A sound is produced by plucking a string in a musical instrument. Then the velocity of wave in the string is equal to velocity of sound in the string. The frequency of the waves in the string is equal to the frequency of the sound produced. Of course, option B will be valid. The frequency of the waves in the string is equal to the frequency of the sound produced. The wave in the string is progressive. The tension in the string varies from point to point. So therefore, the correct option for that question number 27 is B. The frequency of the waves in the string is equal to frequency of the sound produced. So that is option B. Speed of sound waves in a fluid. V is equal to square root of E by rho. For solids, modulus of velocity, it is replaced by Young's modulus. For liquids and gases, it is replaced by B by rho. That is bulk modulus. That is question number 28. Speed of sound waves in fluid is directly proportional to square root of the bulk modulus of the medium. You just observe this relation given now. V is equal to square root of B by rho. V is directly proportional to square root of bulk modulus, and it is inversely proportional to square root of the density. Second one, inversely proportional to bulk modulus of the medium, directly proportional to density of the medium, inversely proportional to the density of the medium, but it is inversely proportional to square root of density of the medium, and it is directly proportional to the square root of the bulk modulus of the medium. So therefore, correct option is A. So it is directly proportional to square root of the bulk modulus of the medium. Figure given shows a sinusoidal wave on a string. If the frequency of the wave is 150 Hz, what is the velocity and wavelength of the given wave? So you just observe in the diagram. So totally you are having two complete waves, crest trough, another one you are having only half of the wave. The length of a single wave can be taken as wavelength. So therefore, since you are having 2.5 wave, so now totally you will have 5 by 2 lambda, or just 2.5 lambda is equal to 20 centimeter. From the diagram, you are having a 2.5 wave, and if the length of each wave is lambda, so therefore you get 2.5 lambda. Crest and trough, totally two waves, 2 times the wavelength, and only crest half of the wavelength. Therefore, 5 by 2 lambda or 2.5 lambda is equal to 20 centimeter. Lambda is equal to 20 by 2.5 or 200 by 25. So we get 8 centimeter or 0.08 meters. That is a wavelength. And if the frequency of the wave is f is given as 150 Hz. What is the velocity and wavelength? We have already found out it is 0.08 meter. We are supposed to find the velocity. V is equal to f lambda 150 into 8 centimeter, 8 into 10 power minus 2. So 150 into 8, it is 1200 into 10 power minus 2. Upon removing the power, you will get 12 meter per second. So that is the V value. So wavelength is 0.08 and the velocity is 12 meter per second. So therefore the correct option is D. So wavelength comes out to be 0.08 meters and velocity is 12 meter per second. Question number 30. If the bulk modulus of water is 2100 megapascal, what is the speed of sound in water? Bulk modulus is given. So we have the relation V is equal to square root of B by rho, where B is the bulk modulus and bulk modulus of water and rho is the density of the water. So density of the water, it is around 1000 kg per meter cube. What is 10 power 3 kg per meter cube. V is equal to square root of 2100 megapascal, 2100 into 10 power 6 mega, density 10 power 3. V is equal to square root of into 10 power 3. Just make a perfect square number power 210 into 10 power 4. Square root of 210. Square root of 225 is 15. In the sense, its value will be greater than 14 and less than 15. Now let me consider its value as around 14.5. the root of 210, it is greater than 14 but less than 15. Let me consider it as 14.5 into root of 10 power 4 is 10 power 2. Therefore, we get 1450 meter per second. So therefore, you will get the correct option as A. So 1450 meter per second. So next, let us move to question number 31. A transverse harmonic wave on a string is described by y is equal to y of x comma t is equal to 3 sine 3060 plus 0.018x plus pi by 4, where x and y are in centimeter and t is in second. Which of the following statements is incorrect? So among the 4 statements given here, so 3 will be valid and 1 is false. So we are supposed to find which is the false statement or incorrect statement. So the given equation, y of x comma t is equal to 3 sine 3060 plus 0.018x plus pi by 4 a sine omega t plus kx plus 5, where pi is the angle, pi by 4. Now when you just compare this equation, the standard relation, the wave is traveling in negative x direction. So generally, if it is y is equal to a sine omega t minus kx, this is along positive x direction. It is equal to, next equation, y is equal to a sine omega t plus kx. This is along negative x direction. So therefore it is, since you are having plus here, so therefore the wave is traveling in negative x direction. It is true. The amplitude of the wave is 3 centimeter. So in the problem it is given that x and y are in centimeter. So when you compare this relation with this one, you will get amplitude as 3 centimeter. So of course option D is also right. The speed of the wave is 20 meter per second. The frequency of the wave is 9 by pi hertz. Now let us just find out what are the values of the speed and the frequency. So when you compare these two relations, you get omega as 36 radian per second. 2 pi f is equal to 36. So f is equal to 36 by 2 pi, or f is equal to 18 by pi hertz. But it says that frequency is 9 by pi hertz. That is a false statement. Now let us just find out what is its velocity now. So now from this relation, k is 0.018. 2 pi by lambda is equal to 0.018. Lambda is equal to 2 pi by 0.018. B is equal to f lambda. F is 18 by pi into 2 pi. 0.018 just now we consider as 18 into 10 power minus 3. 18, pi and pi gets cancelled. So let over here it is given as another one, it is given as centimeters. So therefore this is centimeters. So many centimeter, or this should be taken as 2 pi into 10 power minus 2 by 0.018 meters. Just I will multiply this one by 10 power minus 2, because it says that x and y are in centimeter. So therefore wavelength, it carries the unit centimeter here. So therefore it is converted to meter. That is 2 pi by 0.018 into 10 power minus 2 by 0.018. If this value is taken, this is in centimeter. It is converted to meter, 10 power minus 2. is equal to 2 into 10 power minus 3, it becomes 10 power plus 3, and already you are having minus 2, therefore you get 10 power 1. So therefore it is 20 meter per second. So of course option C is also true statement that the speed of the wave is 20 meter per second. So therefore the incorrect statement is D. The frequency of the wave is 9 by pi hertz, but the frequency of the wave is found out to be 18 by pi hertz. So therefore the correct option for this question is D. That is the incorrect statement. The frequency of the wave is 9 by pi hertz. The ratio of the velocity of sound in hydrogen, gamma is given, it is 7 by 5, that is the ratio of specific heat capacities. So that in helium, gamma is 5 by 3, at the same temperature is, question number 32, the ratio of the velocity of sound in hydrogen, so ratio of specific heat capacities is given as 7 by 5, so that in helium, gamma is given as 5 by 3, at the same temperature is. So we should consider at the same temperature. V is equal to square root of gamma P by rho. We have PV is equal to 40. Ideal gas equation. P is equal to 40 by V. V is equal to square root of gamma RT by rho into V. In the denominator are having the product of density and volume. So generally density is equal to mass by volume. Mass is equal to density into volume. Therefore you get V is equal to square root of gamma RT by M. Okay, now let us go to the present problem now. At the same temperature, okay, T remains same, R is constant. So therefore V is proportional to square root of gamma by M. Gamma by M. Okay, now let us move to hydrogen now. The ratio of the velocity of sound in hydrogen gas to that in helium. So one is hydrogen to helium, VH by VHE is equal to square root of gamma of hydrogen by gamma of helium, because V and gamma are directly proportional, but V and mass are inversely proportional. Mass of helium by mass of hydrogen, square root of gamma for hydrogen, it is 7 by 5 divided by 5 by 3 multiplied by helium 4 hydrogen 2 is equal to square root of 7 by 5 into, take the reciprocal, 3 by 5 into 4 by 2. Two ones are 2, twos are square root of 7 into 3, 21 into 2, it is 42 by 25, or this is equal to square root of 42 by 5. So therefore we get option C here. So hydrogen gas, I have considered mass as 2 units, helium mass is taken as 4 units. Gamma for hydrogen is 7 by 5, for helium it is 5 by 3. Upon taking the reciprocal and multiplication, we get 7 by 5 into 3 by 5, multiplied by 4 by 2, it is nothing but 2. 7 into 3, 21. 21 into 2, we get 42. 5 into 5, 25. Root of 25 is 5. Therefore, we get square root of 42 by 5. So therefore, the correct option is C. Square root of 42 by 5. So question number 33. A tuning fork A of frequency 512 Hz produces 5 beats per second when sounded with another tuning fork B of unknown frequency. Bit frequency for the first case it is given as 5 beats. So bit frequency it is given as 5 and a tuning fork A of known frequency F is given as 412 with another tuning fork B of unknown frequency. So now Fx it is given by F plus or minus Fb. Fx is equal to F plus Fb, that's equal to 512 plus 5, you get 517. One is F minus Fb, 512 minus 5, you get 507 Hz. One is Fx is equal to F plus Fb or F minus Fb. 512 plus 5, 517. F minus Fb, 512 minus 5 is equal to 507. Now what is happening is, if B is loaded with wax, the number of bits is again 5 per second. When the tuning fork B is loaded with wax, if it is loaded with wax, automatically the frequency of B decreases because it is loaded with wax. After loading with wax, once again, if they are sounded together, once again the bit frequency Fb dash once again it comes out to be 5 beats per second. So now we should find what is the frequency of the tuning fork B before it was loaded. Okay, now let us come back to this concept here. Now let us consider the unknown frequency Fx, it is 517 Hz before loading. If it is taken 517 Hz before loading, after loading generally its frequency it decreases. Its frequency decreases. When it is sounded once again the bit frequency is 5. If you consider this 507, if you consider 517, suppose if it is loaded with wax, now let me consider its frequency decreases, it comes out to be around 507 Hz, let me consider. Suppose if this is considered, second case, after loaded with wax, so this comes out to be around 597, let me consider. Sorry, it is 497 Hz. I am considering both the cases here. This is before loading with wax, that is Fx is either F plus Fb or F minus Fb, 517 and 507. Suppose if B is loaded with wax, its frequency decreases. Once again, when A and B are sounded together, once again the bit frequency is 5 bits per second now. If 517 is taken after loading with wax, let us consider if its frequency reduces to 507. But here known frequency is 512. Once again 512 minus 507 you get 5. If it is taken 497, suppose if this is 507 before loading and if this is 497 after loading, if you find the difference between these two, 512 minus 497, we cannot match for 5 Hz. But if this is taken as 507 and if this is taken as 512, you get the bit frequency as 5 even after loading with wax. But if loaded by wax, automatically frequency decreases. That's why I consider its frequency as 497 Hz. Just have given on random value here. But when you take the difference between these two, Why I have taken 10 difference is, first also there is bit frequency 5, second case also bit frequency 5. 507, 497. After loading with wax, if this value is considered, its frequency should decrease to 497. But when you take the difference, you won't match as 5. But if you take these two, 507, 512, automatically you get 5. This is after loading, this is before loading. So therefore, the frequency of the tuning fork B before it loaded is 517 Hertz. 517 Hertz before loading. Because after loading, automatically its frequency decreases to 507. If you consider, then 512 minus 507, once again you will get the bit frequency as 5. But in the second case, if you consider 507 as the initial frequency, after loading, if you consider 497, but when you consider the difference between these two now, you won't get 5 there. So therefore, the frequency of the tuning fork B before it was loaded, it is considered as 517 Hertz. So just I will repeat once again. Initial case bit frequency is 5. Frequency of the known tuning fork is 512. Unknown, it is given by f plus or minus fb. So either it may be f plus fb or f minus fb. If it is f plus fb, 570. F minus fb, it is 507. But once tuning fork B is loaded, here fx is nothing but the tuning fork B, that is unknown. Its frequency should decrease. Now if you consider 570, let me consider its value decreases to 507. Once again, when you sum together, if it is 512 and 507, you get 5. But if its frequency decreases, let me consider it is 497. Here also I have considered the range as 10 degrees, here also 10 degrees. But when you match these two, you won't get 5. So therefore, the frequency of the tuning fork B used to be 517 Hertz. So question number 34. Which of the following properties of a wave is independent of others? Velocity, frequency, amplitude and wavelength. So while studying the properties of the waves, we have seen that the wave velocity through a material medium, it depends upon the elasticity and the density of the medium. So therefore, there is a relation between the wavelength, velocity and frequency. But the wave velocity depends upon the elasticity and the density of the medium. So therefore, velocity is independent of the others. Therefore, option A is the correct option for the question number 34. Out of the following gases, under similar condition of temperature and pressure, the velocity of sound will be maximum in. So just consider the same little relation. V is equal to square root of gamma RT by M. All are diatomic gases. That is hydrogen, nitrogen, oxygen and chlorine. Gamma remains same. R is universal gas constant. R remains same. At same temperature, T also remains same. So therefore, V is inversely proportional to square root of the mass. Hydrogen gas 1h2, nitrogen 714, oxygen O8 16, chlorine 17 34. V is inversely proportional to square root of the mass. If M is small, V will be maximum. It is given that out of the following gases, under similar condition of temperature and pressure, the velocity of sound will be maximum in. Since hydrogen has the minimum mass, speed will be maximum in hydrogen. So therefore, we get option A. So in the hydrogen, the velocity of sound will be maximum. A man standing between two parallel hills claps his hand and hears successive echoes at regular intervals of 1 second. If velocity of sound is 340 meters per second, then the distance between the hills is. So let us consider two hills. A person is standing in between. We don't know where he is standing. Let us consider from here to here it is x, and from here to here the distance is y. Claps his hands and hears successive echoes. Echo is nothing but reflection of sound. If you want to perceive the echo, the sound should travel another distance x here. So therefore totally, for perceiving the echo, total distance traveled is x on this side. On this side, the total distance traveled is 2y. This is for perceiving echo, 2x and 2y. But the distance between the two hills will be x plus y only. But for perceiving the echo, echo is nothing but reflection of sound. Once it claps, sound should reach this hill, it should be reflected, once again it should perceive. So therefore the distance traveled by the sound to perceive the echo by the person, it will be 2x and this is 2y. But the distance between the two hills will be x plus y. Now let us consider, here the time taken is t1 and here the time taken is t2. T1 is equal to 2x by v. T2 is equal to 2y by v. This is time T1 for hearing the echo from this hill. This is time T2 for perceiving the echo from another hill. 2x, it is the distance covered by the sound for perceiving echo by the person. And another one is 2y. Now the distance between the two hills, it is x plus y is equal to, from this relation, so now I can write x as t1 into v by 2, y as t2 into v by 2. So here the total distance is taken as 2x and 2y for perceiving the echo. But the distance between the two hills is x plus y only. But perceiving the echo, x plus x 2x, y plus y 2y. V is the speed of the sound here. And t1 for perceiving the echo from the first hill, and t2 for perceiving the echo from the second hill. Now the total distance between the two hills, that is x plus y is equal to t1 into v by 2 plus t2 into v by 2. This is equal to v by 2 is common, t1 plus t2. Here's the successive echoes at regular intervals of 1 second. Now let us consider he perceives the echo from this first hill after 1 second. And he perceives the echo in the next successive second, in the sense, for the second case the total time should be taken as 2 seconds. In the successive, first echo it is at the first second. Second echo after 1 second means total time becomes 1 plus 1, 2 seconds. So therefore v by 2, 340 by 2 into 1 plus 2. Successive seconds. For the first echo it is the first 1 second. For the next echo it is the next second, but the first plus second second. Therefore it should be 1 plus 2. 170 into 3. Therefore we get 510 meters. That is the distance between the hills. 510 meters. Just I will illustrate once again. Now let us consider two hills. Person is in between the two hills. He is at a distance x from this first hill, and he is at a distance y from the second hill. If you want to perceive the echo, once he claps, sound travels, it reaches the hill, it will be reflected, and once again he perceives the echo. Therefore distance for perceiving the echo, it should be taken as x plus x to x. Similarly here it is y plus y to y. Let t1 be the time taken for the echo from the first hill, and t2 be the time taken for the echo from the second hill. t1 is 2x by v, t2 is 2y by v. That is by taking this relation, velocity is equal to displacement by time, or time is equal to displacement by velocity. From these two equations, you will get x as t1 into v by 2, y as t2 into v by 2. Now the distance between the two hills, here it is x, this is y. So therefore x plus y is equal to t1 into v by 2 plus t2 into v by 2. You will get v by 2 into t1 plus t2. 340 by 2, t1 plus t2. He is perceiving the echoes at regular intervals of 1 second. First he perceives the echo at the first second. Next at the next second, in the sense, you should consider the total time for t2, that is 1 plus 1, it becomes 2 seconds. Therefore, the total distance between the two hills is 510 meters. Therefore, you get option C. The stationary wave y is equal to 2a sin kx cos omega t in a stretch string is the result of superposition of y1 already as given. Y1 is equal to a sin kx minus omega t. Since you are having negative sign, so it moves along the positive x direction. And if you consider another wave which is moving in the negative x direction, it will be given by y2 is equal to a sin kx plus omega t. So therefore, you will get option B here. One wave is along positive x-axis, another wave should be along negative x-axis because there is generation of stationary wave. For the generation of stationary waves, both the waves should be traveling in opposite direction with the same frequency and amplitude with the same speed. So therefore, the correct option for question number 37 is B. That is y2 is equal to a sin kx plus omega t. So it is option B. So question number 38. A steel rod of length 100 cm is clamped at the middle. The frequency of the fundamental mode for the longitudinal vibrations of the rod is speed of sound in steel. It is known as 5 km per second. A steel rod of total length L is equal to 100 centimeter, means it is nothing but 1 meter, is clamped at the middle. If it is clamped at the middle, generally a node will be generated at the middle because there the particles have restricted moments, and here you will have antinode at the free end and you will have antinode at another free end. But where it is clamped, there you will be having a node. In the fundamental mode, you will be having antinodes at the free ends. The distance between two antinodes, it is lambda 1 by 2. If lambda 1 is the fundamental wavelength, so then the distance between the two antinodes, it is taken as lambda 1 by 2. L is equal to lambda 1 by 2. Lambda 1 is equal to 2L, or lambda 1 is equal to 2 meters. This is the fundamental wavelength. And he has given the speed as V. It is 5 km per second. 5 into 10 power 3 meter per second. So we are supposed to find the frequency of the fundamental mode. V is equal to F lambda 1. F is equal to V by lambda 1. 5 into 10 power 3 by 2. We get 2.5 into 10 power 3, or we get 2.5 kilohertz. So therefore we get option C here. So since the rod is clamped at the middle, there is generation of node. At the free ends, generally there will be generation of antinodes. So in this format. Antinode, this is the fundamental mode. If total length is 1 meter, distance between two antinodes is lambda 1 by 2, therefore L is taken as lambda 1 by 2, or lambda 1 is 2L, or lambda 1 becomes 2 meters. And he has given the speed 5 km per second. It is 5 to 10 power 3 meter per second. So we have the relation V is equal to F lambda, or F into lambda 1, or F is equal to V by lambda 1. So therefore we get 2.5 kilohertz. When sound is refracted from air to water, which of the following quantities remain unchanged? Refracted, it travels from one medium to another medium. See, when a wave travels from one medium to another medium of different optical densities, wavelength and velocity changes, but frequency remains constant. So when wave propagates or travels from one medium to another medium of different optical densities, wavelength and velocity changes, but frequency remains constant. So therefore frequency remains constant, remains unchanged frequency. That is option D. A pipe 30 cm long is open at both ends. Which harmonic mode of the pipe resonates at 1.1 kilohertz? Question number 31. A pipe 30 cm long is open at both ends. Which harmonic mode of the pipe resonates at, so there is a small mistake there, T, at 1.1 kilohertz source? Speed of sound in air, it is 330 meter per second. It is open at both ends. So generally for open pipe, fundamental frequency f1, it is given by V by 2L. This is for open pipe. f1 is equal to 330 speed, 330 by length 30 centimeter, 30 into 10 power minus 2, 30 into 10 power minus 2. f1 is equal to hello, sorry, ಏನು ಗೊತ್ತಿಲ್ಲ, ನಮ್ಮ ಕ್ಲಾಸಲ್ಲಿ ಇದೆ ಮತ್ತೆ ಮಾಡ್ತಿದ್ವಿ. So now the fundamental frequency in case of open pipe, it is given by 330 by 30. Length is given as 30 centimeter. So therefore 330 by 30 into 10 power minus 2. So it 3 ones are 3 11s are 11 into 10 power 2 or 1.1 into 10 power 3. 1.1 kilohertz. So now you are supposed to find which harmonic mode of resonates at 1.1 kilohertz. Sorry, just I have left 2 here. So this is taken as 2 times. So you get the value as 11 by 2. So you get f1 as 5.5 into 10 power 2. So this V is 330. So 11 by 2 will get 5.5 to 10 power 2 or 550 hertz. So now this is a fundamental frequency. So just I had left 2 here. So when you consider 2 here, you will get 11 by 2, it is 5.5 to 10 power 2 or you get 550 hertz. This is the fundamental frequency. Since it is open pipe, in open pipe, f1 is to f2 is to f3 is equal to 1 is to, so it is an open pipe, it is 1 is to 2 is to 3 is to 5. So it has both odd and even harmonics. If it is closed pipe, for closed pipe, f1 is to f2 is to f3 is equal to 1 is to 3 is to 5. This is for closed pipe. For open pipe, f1 is to f2 is to f3 is equal to 1 is to 2 is to 3 is to 5. Now if you find f2, So F2 you get twice F1. This is equal to 2 into 550 hertz. So therefore you get 1100 hertz, or you get 1.1 into 10 power 3 or 1.1 kilohertz. So now he has asked which harmonic mode of the pipe resonates at 1.1 kilohertz. Fundamental frequency, it is nothing but the first harmonic. First overtone of the second harmonic, it is 1.1 kilohertz. Therefore the second harmonic vibrates with 1.1 kilohertz. Therefore the option is B. That is the second harmonic. This is the first harmonic. This is the second harmonic. F2 it is termed as first overtone or second harmonic. First overtone or second harmonic. So therefore the correct option for this one is second. Just I will explain once again. For open pipe, the fundamental frequency is given by V by 12. Upon solving, fundamental frequency comes out to be 550 Hz. In open pipe, the overtones of the harmonics of the fundamental, it has both odd and even harmonics. F1 is to F2 is to F3 is equal to 1 is to 2 is to 3 is to 4 and so on. Now if you consider the first overtone of the second harmonic, F2 can be taken as 2F1. So you get 1100 Hz or 1.1 kilohertz. Therefore, the second harmonic resonates at 1.1 kilohertz. Therefore, the correct option is B. So next, let us move to 41. The frequency of a tuning fork is 256 Hz. It will not resonate with a fork of frequency. So in this present problem, there is a mistake in that option A. Option A, it should be taken as 768 Hz. So there is a mistake in this option A. It should be taken as a 768 Hz. So now initial frequency. Now let me consider F1 is 256 Hz. F2, next harmonic, twice F1, F3, thrice F1, F4, 4 F1. This becomes 512 Hz. This is nothing but 3 into 256. So 3 into 6, 18. 3 place of 15, 6, 1. 3 to the 6, 768 Hz. So now this is 4F1. 512 plus 512, you get totally 1024 Hz. In the option you are having, this first option it should be taken as 768, it is not 786. 768. Option B 738, option C 512, option D 256. So therefore it will resonate with 256, 512, 768, 1024 Hz. But you are having option B as 738 Hz. Therefore it will not resonate with the frequency of 738 Hz. Therefore the correct option is B. So please you change this option A to 768 Hz. It is not 786. So the given tuning fork it resonates with 256, 512, 768 and 1024. But in the given options you have 768, 512 and 256. But 738 it doesn't resonate with 738. Therefore it will not resonate with the fork of frequency 738 Hz. Please in this problem option A is 768 Hz. It is not 786. Next let us go to 42. A band emits ultrasonic sound of frequency 100 kilohertz in air. If this sound meets a water surface, the wavelengths of reflected and transmitted sound are, reflection means bouncing back to the same medium. So therefore you should consider the air medium for reflection. But for transmitted, first medium is air, second medium it should be treated as water. Wavelengths of reflected and transmitted. First let me consider reflected. Reflected means it is bouncing back to air medium itself. So now frequency in air is 100 into 10 power 3 hertz. He has given as 100 kilohertz. That is frequency in air. Speed of sound in air. Let me consider speed of sound in air as VA. It is given as 340 meter per second. 340 meter per second. So here you can find out its wavelength by applying V is equal to F lambda. Lambda is equal to, this is in air medium, that is the wavelength of the reflected light. 340 divided by 100 into 10 power 3. 340 into 10 power minus 5, 100 can be taken as 10 power 2, 10 power 2, 10 power 3, 10 power 5, if it is taken to numerator, it becomes 10 power minus 5. So upon removing the power, you get 0 point, so 1, 2, 3, 0 point then, or let us it is given in millimeter. Okay, now let me consider this one as 3.4 into 10 power minus 3, 0.4. So I have shifted decimal by 2 digits, power reduces by 2, therefore we get 3.4 into 10 power minus 3, or we get 3.4 millimeter. This is the wavelength of the reflected light in air medium. Now transmitted. See, when a wave travels from one medium to another medium, wavelength and velocity changes, but frequency remains constant. By using this equation itself, V is equal to F lambda, you can consider V is proportional to lambda. VA by VW, that is in water medium, lambda A by lambda W. So now we are supposed to find, so transmitted, wavelength of transmitted, that is lambda V, wavelength in water, is equal to VW into lambda A by VA. So now the speed in water is known as 1500, wavelength in air 3.4 into 10 power minus 3 by VA 340. 1500 into, this can be taken as 340 into 10 power minus 5 divided by 340. 3.4, just I have considered 340 and I have raised the power by minus 2. 340 gets cancelled. You get 1500 into 10 power minus 5. So upon taking in millimeter, you get this one as 15 into 10 power minus 3 meter, or you get 15 millimeter. So therefore, wavelength of reflected sound wave is 3.4 meter and transmitted sound wave is 15 millimeter. So therefore, we get option C. It is 3.4 millimeter and 15 millimeter. So reflected means in the same medium. That's why I have considered velocity in air medium. If it is transmitted, frequency remains constant, but there is change in wavelength and velocity. Upon taking this relation, you can find what is the wavelength in water medium. It is 15 millimeter. Therefore, option C is the correct solution for the one. Next, question number 43. The phenomenon of echo is an example of, it is nothing but reflection. Echoes are generated due to reflection of sound from rigid boundaries. So therefore, it is an example of reflection. So option A. Which of the following statements is incorrect for a stationary wave? Every particle has a fixed amplitude which is different from the amplitude of its nearest particle. Of course, this is a true statement. All the particles cross their mean position at the same time because they have all the particles within a loop or segment, they have same phase. All the particles are oscillating with same amplitude. So just observe the first one and the third one. Here, which is different, this is valid, but here it is the same amplitude. So therefore, which is different, which is incorrect? Which of the following statements is incorrect? First statement is true, second statement is true, but third statement, he says that all the particles are oscillating with same amplitude. But amplitude varies from one particle to another particle. That is, every particle has a fixed amplitude which is different from the amplitude of its nearest particle. Option C is the false statement. D. There is no net transfer of energy across any plane. because stationary waves, they won't transfer energy in any direction. Therefore, there is no net transfer of energy across any plane. Therefore, the incorrect option is C. That is, all the particles are oscillating with same amplitude. This is the incorrect option of the statement. When a string is fixed at its both ends, vibrates in 1 loop, 2 loops, 3 loops and 4 loops, the frequencies are in the ratio. In case of a stretched string, F1 is to F2 is to F3 is to F4, it's 1 is to 2 is to 3 is to 4 and so on. So therefore you get option B here. 1 is to 2 is to 3 is to 4. A pipe 17 centimeter long. Question number 46. A pipe 17 centimeter long is closed at one end. Which harmonic mode of the pipe resonates at 1.5 kilohertz source? Speed of sound in air 340 meter per second. So it is a closed pipe. Fundamental frequency will be given by V. F1 is equal to V by 4L. F1 is equal to V. Speed it is given as 340 by 4 into length is 17 centimeter. 17 into 10 power minus 2 meters. F1 is equal to 17 ones are 17 2s are. So we get 20 into 10 power 2 by 4. 20 by 4 is 5 into 10 power 2. So therefore we get 500 hertz. This is a fundamental frequency. In case of a closed pipe, F1 is to F2 is to F3 is equal to 1 is to 3 is to 5. Overtones in a closed pipe are odd harmonics of the fundamental. F2 is equal to 3 times F1. 3 into 500 will get 1500 hertz. 1.5 kilohertz. It is nothing but 1005 hertz. 1.5 into 10 power 3. That is nothing but 1000. So therefore we get 1500 hertz. But here, generally while discussing, we had considered this is the second harmonic or the first overtone. But since F2 is equal to 3 times F1, here it is 3 times F1. So while dealing with the closed pipe, this should be taken as third harmonic because it is F2 is taken as 3F1. But if you consider the open pipe, you will get F1 is to F2 is to F3 is equal to 1 is to 2 is to 3 and so on. Here F2 is twice F1, F3 is thrice F1. Now this is the second harmonic and this is the third harmonic. By taking this one as a reference, since here F2 is 3 times F1, now this should be treated as the third harmonic. So therefore, the correct option for 46 is third. In the option, they have not given second one also. So therefore, it should be taken as third here. Why it's third in the sense F2 will be equal to 3 times F1. So therefore, since it is 3 times F1, it should be treated as the third harmonic. A resonating air column shows resonance with a tuning fork of frequency. Question number 47. A resonating air column shows resonance with a tuning fork of frequency 256 Hz at column length 33.4 centimeter and 101.8 centimeter. The speed of sound in air is. Generally, this concept of this equation will be used in the laboratory to find the velocity of sound. That is resonance column experiment, which is given by the relation V is equal to twice F into L2 minus L1. V is equal to 2 into 256 into L2. 101.8 minus 33.4. This is centimeters. So 101.8, 33.4. 4, 11, 3, 9 minus 3, 68.4. So it is 512, 2 into 256, 512 into 68.4 into 10 power minus 2, or 512 into 0.684. Remove the power now. I have converted the length to meter. 0.684. Approximately, you just round this one to 0.7. 5 into 0.7. It comes out to be 350. So therefore, it comes out to be around 350 meter per second. So you just round this one to 0.7. If it is rounded to 0.7, so 500 into 0.7, it comes out to be 350. So there is no solution in the range of 350 or 360. Therefore, correct option will be 350 meter per second. This equation generally we will use in the laboratory in the resonance column to find the speed of sound, where L1 is the first resonating length and L2 is the second resonating length. V is equal to twice F into L2 minus L1. In stationary waves, nodes are the points where there is nodes and you are having antinodes. Question number 48. In stationary waves, nodes are the points where there is. So now we are supposed to discuss the point where the nodes is generated. Minimum displacement. But if it is minimum displacement, you will have a maximum pressure change. If it is antinode, maximum displacement, minimum pressure change. But if it is a node, minimum displacement and maximum pressure change. At the node, minimum displacement. Displacement will be minimum, but there is maximum pressure change. In antinode, it is quite vice versa. Maximum displacement and minimum pressure change. Therefore, the correct option is B for question number 48. Question number 49. Which of the following statements is correct? So you should find the true statement now. Among these four, you should find the correct statement. The distance between any two consecutive antinodes or nodes is lambda by 2. But we have studied that the distance between any two consecutive nodes or antinodes is lambda by 2. First statement is false. The distance between a node and adjoining antinode is lambda by 4. Of course. The second statement is true. The distance between a node and an adjoining antinode is lambda by 4. In the open end is a node. Generally at the open end there is a formation of antinode. In the closed end there is an antinode, but generally at the closed end we are having a node. So therefore statements 1, that is A, C and D are incorrect, but B is the true statement. That is the distance between node and adjoining antinode is lambda by 4. Therefore the correct option for that question is B. So next let us move to question number 50. A wire is stretched between two rigid supports, vibrates in its fundamental mode with a frequency of 50 Hz. The mass of the wire is 30 grams and its linear density is 4 into 10 power minus 2, that is kg per meter. So there is a mistake here. So linear density 4 into 10 power minus 2 kg per, that is mass per length, kg per meter. There is a small mistake in typing the unit there. The speed of the transverse wave at the string is, we are supposed to find what is the speed of the transverse wave. In its fundamental mode with the frequency of fundamental frequency, it is given as 50 Hz. Mass of the wire 30 grams, 30 into 10 power minus 3 kg. and its linear density is mu 4 into 10 power minus 2 kg per meter. So generally mu will be taken as mass per length. Length is m by mu. So mass 30 into 10 power minus 3 mu 4 into 10 power minus 2. So let this one as 4, 15, we get 7.5. 7.5 into 4, we get 30 into 10 power minus 1, or we get 0.75 meter. This is the length now. So just I have found out the length L value, 0.75 meter. The speed of the transverse wave. So generally in a fundamental mode of vibration, in a stretched string, you get a single loop, node and node. If L is taken as a distance, and if lambda 1 is a fundamental wavelength, so then lambda 1 by 2 is the distance between two nodes. So from this diagram, you can write L is equal to lambda 1 by 2, or lambda 1 is equal to 2L. That is the fundamental mode of vibration of a stretched string in its lowest possible mode. There is formation of a single loop or segment. So if L is the total length of the string and lambda 1 by 2, it is the distance between the two nodes. Therefore, fundamental wavelength can be taken as lambda 1 is equal to 2L, or lambda 1 is equal to 2 into length is 0.75. So therefore, we get 1.5 meter. That is the fundamental wavelength. Fundamental wavelength. And he has given the fundamental frequency, that is 50 Hertz. So now let us find what is its velocity. V is equal to F 1 into lambda 1, 50 into 1.5. We get 75 meter per second. So that is the speed of the transverse wave, 75 meter per second. So it is option C. 75 meter per second. A guitar string, next question. A guitar string is 90 centimeter long and has a fundamental frequency of 124 Hertz. To produce a fundamental frequency, so there a term is not given. So to produce a fundamental frequency 186 Hertz. To produce a fundamental frequency 186 Hertz, the guitar should be pressed. So there, this 186 Hertz has been not typed there. So now you should consider to produce a fundamental frequency 186 Hertz, the guitar should be pressed. See, in a string, so generally we have the frequency as fundamental frequency 1 by 2L into root of T by mu. F and L are inversely proportional here. Where tension in the string and mass per unit length, let us consider constants. For T and mu constants, F is inversely proportional to L. Or F1 L1 is equal to F2 L2. So now he says that a guitar string is 90 centimeter long and has a fundamental frequency of 124 Hertz. So 90 centimeter and 124. 124 into 90. Since solution is in centimeter, I have considered L1 in centimeter. To produce a fundamental frequency of 186 Hertz, 186 into L2. Now L2 is equal to 124 into 90 by 186. 3 30s are, 3 6s are, or let me consider this one as, okay, 3 6s are, 3 2s are, 3 into 30 90, 3 6s are 18, 3 2s are 62, 62 1s are, 62 2s are. So therefore we get L2 as 2 into 30, we get 60 centimeter. For given P and mu constant, F is inversely proportional to L. Therefore, F1 L1 is equal to F2 L2. So you will find the L2 as 60 centimeter. So in the problem, to produce a fundamental frequency, a term has been left there. It should be 186 hertz. So therefore, F2 should be taken as 186. Upon solving, you will get the length as 60 centimeter. So you will get option A as a solution here, 60 centimeter. In an organ pipe of length L, open at both ends, the fundamental mode has a frequency. So it is open at both ends. In the fundamental mode of vibration, in case of an open pipe, so frequency will be given by V by 2L. And all harmonics are present because in open pipe, F1 is to F2 is to F3 is equal to 1 is to 2 is to 3. That is, you have both odd and even harmonics. So therefore, V by 12 and all harmonics are present. So therefore, we get option C. Question number 53. A tuning fork of frequency 440 Hz resonates with a tube closed at one end of length. Here also there is a mistake. It is not 1.8, it is 18 centimeter. So it should be considered as 18 centimeter. It is not 1.8. A tuning fork of frequency 440 Hz resonates with a tube closed at one end of length 18 centimeter and a diameter 5 centimeter in fundamental mode. The velocity of sound in air is tube closed at one end. So if it is closed at one end and open at the other end, it should be treated as a closed pipe. In case of closed pipe, the fundamental frequency after applying the end correction, it will be given by F1 is equal to V divided by 4 into L plus E. So this equation, this is after applying end correction, and E is equal to 0.3 times the diameter. So since in the present problem they have given the diameter 5 centimeter, we should apply the end correction. So this is the equation for fundamental frequency in closed pipe after applying end correction. So here we are supposed to find the velocity of sound in air, V. V is equal to F1 into 4 into L plus E. So as given the fundamental frequency 440 into 4 length, it is 18 centimeter. 18 plus, and E should be taken as 0.3 times diameter. 0.3 into diameter is 5. So here I have considered both the lengths in centimeter itself. 440 into 4 into 18 plus. So you get so 5 into 0.3, 1.5. This is in centimeter. 440 into 4 into 90.5 into 10 power minus 2. So 4 zeros are 0, 4 4s are 16, 1, 4 4s are 16, 1760 into 19.5 into 10 power minus 2, or this can be taken as 17.6 into 19.5. So upon multiplying those two terms, so the solution comes out to be 343. Meter per second. So therefore, we get the option as B. It is 343 meter per second. So we are left with another 15 to 16 questions. So we will discuss in our next session.